Alrighty, today we're going to look at finding the missing sides inside of circle geometry. In order to do this, we end up using a lot of your trig, most specifically the Pythagorean theorem, which we saw a whole bunch with triangles, and actually that's what we'll be doing a lot of today is constructing triangles inside of circles. So I figured it'd be worthwhile to just quickly review that good old famous Pythagorean theorem, a squared plus b squared is equal to c squared, wherein a, b, and c are simply the sides of the triangle. For a and b, it doesn't matter which sides you pick, so long as they're not the longest side, which is your hypotenuse here. So I'm just going to pick 3 is a, 4 meters is b, and I've already labeled this side here as c. So at this point now, I just do the simple substitution. I'm going to leave the units off, just to make it a little easier. So 3 squared, because that's my a, plus 4 squared is still going to be equal to c squared. I can't sub anything in because I don't know the values of c. 3 squared is 3 times 3, which is 9. 4 squared is 4 times 4, which is 16, which is still equal to c squared. It is a good idea to keep your equal signs in a nice straight line with each other. 9 plus 16 is 25, which equals c squared. Because we have the c being squared, and we want to find just the value of c on its own, we simply take the square root of both sides. Square root of 25 is both positive and negative 5. And the square root of c is positive and negative c, but we're only interested in positive values because we can't have a negative side length along here. So then this side is 5. Let's see it in a circle. So take a moment to look at the circle here. I have a blue chord that's now black because I've colored on it, which measures the length AB, which is 18 centimeters. I also have this nice red chord here that I won't color over this time, which is from C down to point D here, which is 12 centimeters. So it's not drawn here, but what I'm looking for is the radius of the circle. Now we know the radius can go from the center out to any point. However, we know some stuff about this CD and this AB. So why don't we try and find the radius where we can construct a nice triangle, such as this one here. Now it's not explicitly shown here, but if I draw these little tallies, what I'm saying here is the length from A to D is the same as from D to B. We know this to be true because we have a chord on the circle with a line that runs straight through the center of our circle, right? Which makes it a perpendicular bisector. So if it's a perpendicular bisector, that means it cuts this line in half. Therefore, the length of AD must be equal to half of the length of AB, or AB divided by 2. So this length AD along here, where I'm drawing the squiggles, will actually be equal to 18 divided by 2, which is just 9 centimeters. So I can label this side here as 9. Now I can start using the Pythagorean theorem to figure out the length of my radius, r, which I'll probably end up calling c later. So let's just set it up again. A squared plus b squared is equal to c squared. Again, c must always be the hypotenuse, the longest side. So put a little c right there. And a and b, it doesn't matter which I pick for which. So let's have a look at, let's call this side here A, and this side over here, this 12 centimeters b. So I have 9 centimeters squared plus 12 centimeters squared equals c squared. Now I just start performing the algebra. 9 times 9 is 81, plus 12 plus 12 is 144, which is equal to c squared. Now 81 plus 144 is 225. Let me double check that. 5, 8, and 4 is 12. 1. Yes, 225. Once again, now I simply take the square root of both sides, and c is equal to 15. So down here at the bottom, we should write therefore, 3 little dots in the triangle for therefore, our radius is 15 centimeters. Remember the centimeters because those are the units I'm working with. All right. That's not too shabby. Not too shabby at all. Let's consider a triangle. It's not often we're trying to find the radius of a triangle or of a circle. Most often we know the radius of a circle. Okay. Suppose we knew the radius of the circle was 20 centimeters. And we knew that this chord, again, let's label it AB. Let's call this C and D again, just so we have our spots quite nice. Let's assume that that chord AB is 12 centimeters. And we're trying to find AD. Oh, sorry, I apologize. We're trying to find CD. Well, AD is pretty easy to find. Right? From here to here. Once again, we have a chord that is being perpendicularly bisected by another line. Therefore, we know AD must be equal to half of AB, or AB divided by 2. All right, so that'd be 12 divided by 2, which is 6 centimeters. So now we're trying to find CD. Let's fill in what we do know. We know this side here is 6. We don't know this side, so I'm actually going to call it B. And we know this side here is 20 centimeters. So once again, I'm going to set up the Pythagorean theorem. I'm going to let my A be 6 squared plus my B, I don't know yet, and my C is 20 squared. When I look at this, I realize I've got numbers and letters on the left, and only numbers on the right. In order to get that letter, that B squared all on its own, I end up having to do some subtraction. So your formula, you could have done it before, simply B squared equals C squared minus A squared, or I can start doing the math first. Well, 6 squared is 36, plus B squared, 20 squared is 400. Now I subtract 36 from both sides. And what you do to one side, you always do to the other in algebra. 36 minus 36 is 0. B squared. 400 minus 36 is 400 minus 36 is 4, and that would be 6 and 3. So 364. Then I take the square root of that. B is equal to the square root of 364, which should be not 16. 64 square root. About 19.08. Therefore, the length of CD is 19.08 centimeters. It is worth thinking, most often a question such as this would be water in a pipe. So we might actually be looking for the depth of the water, which might be this part here. So this is my water level. So in order to figure out what that would be, I just recognize the full radius is 20, and this purple bit here is 19.08. Obviously not drawn to scale. So, therefore, slide down, yeah. There we are. So the depth of the water would be 20 centimeters minus 19.08 centimeters, which is equal to 0.92 centimeters. So less than 1 centimeter of water inside of that pipe. Had the pipe been rolled over, let's see here, so unlock it. Had this pipe been, oh, why didn't those shapes come with me? My goodness, sir. All locked in place for some reason. Had this pipe been rolled over this way, and we're talking about the depth of the water in the pipe being way up here, we'd recognize that the water from the center, we have our radius of 20, but then this C to D, this piece that went, this purple piece here, was 19.08. The total depth of the water, in this case, if it would have been flipped over, right, would have been if flipped over, the depth would be the radius plus CD, which in this case is 20 plus 19.08, which is equal to 39.08. And that concludes finding missing sides inside of a circle.